Hi everyone, this is video 8 of the Regents chemistry curriculum, and in this video we're going to be balancing chemical, nuclear, and redox reactions. The objective is to use the laws of conservation of mass, energy, and charge to identify unknown isotopes or decay modes in nuclear reactions, and to calculate the minimum amount of moles of reactants that is necessary to make a desirable product. So let's get started. Here are some questions for you. See if you can tell whether these statements are true or false. In number 4, I tell you that the first part of the statement is true. I'm just concerned whether the second part of the statement is true or false. So pause the video, see if you can answer these questions. If you cannot, please don't worry about it. You should be able to answer these questions at the end of the video. So let's get started. Okay, so we are going to balance equations. Let's start with chemical reactions, and then we'll go on to nuclear reactions, and then we'll go on to redox, or just balancing the charge. Okay, let's read a little bit. Stoichiometry is using mathematics and chemistry. There will be a whole new video just for stoichiometry, so we will not be conducting any stoichiometric calculations here. We'll only be doing simple balancing. We use coefficients to balance reactions. There are a bunch of combustion reactions that we talked about in the previous video. Here they are. So these are all already balanced reactions. We're probably going to balance this one, C3H8, for you. I'm going to show you how I balance this combustion reaction, C3H8 plus O2 yielding CO2 and 4H2O. So this reaction is already balanced. I'm going to show you how I did it. Okay, let's continue reading. Always leave lonely elements to be the last ones balanced. So if there's an element that's by itself, not bonded to other elements, leave it to be the last one balanced. You can always use a half a decimal, like a decimal number, such as 0.5, to balance a single element. And then at the end, you can multiply the entire reaction by 2 to change that 0.5 to a whole number. In this case, would be 1. Keep in mind, we multiply the entire reaction by 2. If polyatomic ions exist on both sides of the reaction, polyatomic ions are those ions present on table E. Take a look at them right here. These are all polyatomic ions. So if you see these polyatomic ions on both sides of the reaction, treat them as one substance. Do not try to split them. So in this case, SO4 is on this side and it's on that side. We treat it all as one. So we say there's one SO4 here and there's one SO4 here. One here and one here. Okay, same thing here for OH. There's actually OH here and there's H2O here, but H2O is simply nothing but HOH. That's what H2O is. Two H's and an O. So H2O is HOH. This is actually the more appropriate way to write H2O. You should not write H2O, you should write HOH, because there's a positive hydrogen that combines with a negative hydroxide ion. Since OH exists on one side of the reaction and H2O, this should say H2O, exists on the other, this reaction can be rewritten as H2SO4 plus MgOH2 yields HOH plus MgSO4. Now we can balance this reaction as follows. So as we can see here, there are two H's on the left side of the arrow, and initially there was only one H. So I put a coefficient 2. Remember, we use coefficients to balance chemical reactions. So I put the coefficient 2 right here. So I can have two H's. But this coefficient 2 does not only affect the number of H's that I have, it distributes to everything else in the compound. So this 2 actually made me get two H's and made me get two OHs. Again, because it's a polyatomic ion that's present on both sides, treat it as one ion. So I have two H's and I have two OHs. Do I have two H's on the left? Yes. Do I have two OHs on the right, on the left as well? Yes. Okay. Now the H's and the OHs are balanced. Now we just got to look at the Mg's. Do I have one Mg on the right? Yes. Do I have one Mg on the left? Yes. Mg's are balanced. Are the SO4s balanced? I have one SO4 on the right, one SO4 on the left. The SO4s are balanced. So everything is balanced now. Okay, let's try to do another example. Maybe we should maybe we should try something like this. Let's do that same equation, or the same reaction that we had initially, where we had propane combined with oxygen to yield carbon dioxide plus water. So now I don't have OH on the left side of the arrow. This is the arrow. I don't have OH on the left side of the arrow. I only have, but I do have H2O on the right side of the arrow. I don't need to rewrite H2O to HOH because the left side does not have OH. So there's no need to rewrite H2O to HOH. So I can balance the OHs together. You only rewrite H2O if one side of the reaction has OH and the other side has H2O. In this case, I don't have to rewrite it, so I leave it alone. So let's try to balance it. Remember, leave lonely elements alone. So this is oxygen, a lonely element by itself. We're going to leave it to the end. We'll balance it at the end. Now, we're going to try to balance the carbons. I have 3 carbons here. I need 3 before the arrow. I need 3 carbons after the arrow. So I'm going to put a 3 here. Next, I have 8 hydrogens here before the arrow. So I'm going to need 8 hydrogens after the arrow. So I'm going to multiply this hydrogen by 4. Now I have 8 hydrogens, 4 times 2, distribute. I have 8 hydrogens after the arrow. I have 8 hydrogens before the arrow. I have 3 carbons before the arrow. I have 3 carbons after the arrow. My carbons and my hydrogens are balanced. Now I will worry about that lonely element, which I left to the end. Let's see how many oxygens I have. On the right side first. On the right side, I have this 3 distributes. I have 3 carbons and I have 6 oxygens. So here I have 6 oxygens. This 4 distributes. I have 8 hydrogens and 4 oxygens. So the total amount of oxygens that's on the right side is 10. The total amount on the left side is 2. So what do? I multiply this oxygen by 5. 5 times 2 gives me 10. I have 10 oxygens on the left, 10 oxygens on the right. The sum of all the oxygens is 10. And everything else is balanced. So this was one way. We didn't have to use decimals for this combustion reaction. And we can double check. We have 1. There's 1 C3H8, 5 oxygens, give me 3 moles of carbon dioxide and 4 moles of H2O. Let's take a look over here at the balanced equations. 1, 5, 3, and 4. So it's all balanced. Now let's try to do the ethanol. Ethanol is maybe ethanol is a little more tricky. Here we go. So ethanol, or actually ethane, just do ethane. So here's ethane, C2H6 plus O2 yields CO2 plus H2O. Again, no need to rewrite H2O to HOH because there's no OH here. Okay, let's try to balance this. Again, leave the lonely element to the end. Leave the oxygen to the end. 2 carbons. I need 2 carbons here. Here we have 2 carbons here. Okay. Next, hydrogens. I have 6 hydrogens here. I need 6 here, so I'm going to multiply this by 3. Next, oxygens. I have distribute that too. I have 4 oxygens here. Distribute this 3. I have 3 oxygens here. 4 plus 3 oxygens gives me a total of 7 oxygens. The other side, I only have 2 oxygens. So I need to multiply this 2 by a number that gives me 7. In this case, I'm going to multiply this O2 by 3.5. Notice I had to use a decimal here. Now, because I used the decimal, I want to make sure that in the Regents is going to ask you to balance the reactions to the nearest, to the least whole number. So here, you're going to have to change that decimal to a whole number, but you cannot just change this O2. You have to change everything in this reaction. So you multiply this entire reaction, every coefficient, notice my words, you multiply every coefficient in this reaction by 2. So you'll end up with this C2H6, you only had 1 of it, now you're going to have 2 C2H6. Plus this O2, you had 3.5 of it, now you're going to have 7 O2. Yields, you had 2 CO2s, now you're going to have 4. Again, I'm multiplying by 2. That's all I'm doing. Plus this 3H2O, now you're going to have 6 H2O. So this will be your balanced reaction. Okay. Now, let's go on to the next concept. Next concept here is about balancing nuclear reactions. Let's read this. Okay, we're going to go back to the previously shown natural and artificial transmutation reactions. Let's take a look. Here, in a nuclear reaction, some of the mass is usually converted to energy, and there's usually some transmutation that takes place. So let's take a look. We started here with aluminum, which has 13 protons and a mass of 27. We added helium to it, which has a mass of 4 and 2 protons. And that gave me phosphorus and a neutron. So to balance this reaction, it's always already balanced. So let's see, the mass on top on the left must equal the mass on top on the right. So 4 plus 27 gives me 31. 30 plus 1 gives me 31. 13 plus 2 gives me 15. 15 plus 0 gives me 15. Let's try to write our own nuclear reaction. So table N as in Nancy. Let's see. Here we go. It will tell you what each radioactive isotope, it will tell you the decay mode of each radioactive isotope. So let's say I'm trying to write a balanced nuclear reaction, or a balanced nuclear reaction that represents the decay of carbon-14. Okay, so carbon-14 produces a beta particle. Let's see what a beta particle looks like. Here it is. So carbon-14. Carbon has a mass of 14. I'm going to put 14 on top. Is going to release a beta particle. The beta particle has this symbol and a mass of 0 and a charge of -1. Carbon, according to the periodic table, I need a number at the bottom, right? And the charge goes at the bottom, or the nuclear charge goes at the bottom. So carbon is number 6 on the periodic table. Therefore, according to EPNA, electrons equal protons equal the nucleus charge equal the atom number. Therefore, carbon has 6 protons. So, going back to the reference tables, now my carbon here is going to have 6 protons. But look, this is not balanced. The mass here is 14, the mass here is 0. So I need to produce something else that has a mass of 14. 14 plus 0 shall equal to 14, which is the same as the 14 that we started with. Now here, the left side has a mass of 6, but the right side, has a charge of 6, but the right side has a charge of -1. So here, I should have a charge of 7, or an atom number of 7. Nuclear charge of 7. 7 protons. Okay? Now I need to know what this element is. It has a number of 7, it's number 7, and has a mass of 14. You don't have to worry about matching the masses. You only have to worry about matching the atom number. So we'll go and look at the periodic table. We see that nitrogen is number 7. So that unknown element that we were looking for is the element nitrogen. So we go back here and we simply just write its symbol, N. And now we have a balanced nuclear reaction. The mass on the left equals the sum of all the masses on the right, and the charge on the left, or the atom number on the left, equals the sum of the charges on the right. 7 plus -1 gives me 6. So this is all we need to know about nuclear chemistry. Now going on, or moving forward to before I move on to the redox reactions, I want to just make sure that you understand that when you balance the nuclear reaction, you're actually saying that in order to produce a certain product, you have to have a certain amount of ingredients. So, for example, if you want to produce 2 moles of water, you need to mix exactly 1 mole of MgOH with 1 mole of H2SO4. These two have to react together. 1 mole of H2SO4 with 1 mole of MgOH will produce 2 moles of water and 1 mole of magnesium sulfate. Okay, if you have half a mole of this and half a mole of this, then you're only going to produce half this quantity and half this quantity. Why is this important? If you're working in the industries and you're trying to produce a product, a certain amount of products, you would definitely need to know exactly how much reactants you have to order. If you order too many reactants, then you're wasting resources. If you order too few reactants, then you can't really produce the quantity that you really desire. So balancing chemical reactions is very, very important. Now, moving on to balancing charges. So redox reactions are simply reduction and oxidation reactions. We're going to talk more in details about what reduction is and what oxidation is, but I'm going to tell you just right now that you need to remember oil rig or oil-ip rigor. Oil-ip rigor. Now, some teachers will probably tell you, Leo the Lion said GR. I don't use that. I use oil-ip rigor. Why? Because oil-ip rigor actually tells you that oxidation is losing electrons at the product side, P for products, while reduction is gaining electrons at the reactant side. Okay? So, oxidation is all about losing electrons, and reduction is all about gaining electrons. If I lose electrons, I have fewer electrons, which means I am going to have a positive charge. If I gain electrons, I'm going to have additional electrons, which means I'm going to have a negative charge. Again, we'll discuss more of that later on. But let's take a look at this reaction here. We have calcium atom, which became a calcium +2 ion, and we have an aluminum ion that became an aluminum 0. So when I balance this, I learned that the total charge, it's already balanced right now, the total charge on the left equals the total charge on the right. Keep in mind, I'm not trying to make aluminum charge on the left equals aluminum charge on the right. No, I'm looking for the total charge. So the total charge on the left equals the total charge on the right. What do we have here? For aluminum, each aluminum is going to lose 3 electrons. So each aluminum has a charge of +3. I have 2 of them. So the charge here is +6. Calcium has a charge of 0. You have 3 of them. The charge remains 0. So the total charge on the left is +6, and 0 gives you 6. Looking on the right side, on the other hand, calcium, each calcium has a charge of +2, meaning each calcium will lose 2 electrons. You have 3 of them. You have 3 calciums, meaning you have a total of 6, a charge of 6. And then aluminum, each aluminum has a charge of 0. You have 2 of them, so it remains as 0. +6 for the calciums, 0 for the aluminums. The net charge on the right is +6. So the charge is balanced. Now that the charge is balanced, all you have to worry about is the number of atoms that you had. So you have 2 aluminums with a +3, and you have 3 calciums with a +2. Now, if you started with 2 aluminums, obviously you're going to end with 2 aluminums. If you ended with 3 calciums, obviously you started with 3 calciums. So I put this 3 here, and I put this 3 here, and I put this 2 here, and the 2 here. First thing I did was actually balance the charge. Well, that's what I cared about. So if I redo this again, I'm going to have this Ca0 plus Al3 plus yields Ca2 plus Al0. When balancing this, first thing I look at is actually balance. First thing I do is balance the charges. The net charge here is +2 and 0. The net charge here is 0 plus 3. So here I have a 3, here I have a 2. I think of the least common multiple. In this case, it would be 6. So I multiply this by 3, and let me just use a different color here. So I multiply this by 3, and I multiply this by 2. Now I have a total of 6, and I have a total of 6. A charge is 6 here. Now I have 2 aluminums here. I want to make sure I have 2 aluminums on the right. I have 3 calciums here. I want to make sure I have 3 calciums on the left. And that's it. That's how we balance charges. Now, if you want to actually write the redox reaction, see who was oxidized and who was reduced, let's take a look at it. We started with a calcium atom. We started with 3 calcium atoms that had initial charge of 0. So I'm starting with 3 calciums that have a charge of 0. And those 3 calciums became 3 Ca plus 2. They became 3 calciums with a charge of plus 2. Okay, now you have to figure out whether this is oxidation or reduction. If you started with 0 and you became positive, did you gain or did you lose electrons? If you started with a charge of 0 and then your charge became positive, that means you have fewer electrons, which means you lost electrons. You got rid of electrons. And if you lost your electrons, you're talking about oxidation. And in this case, we're going to be thinking of OILIP. Oxidation is losing electrons at the product side. How many electrons did you lose? Well, each calcium atom lost 2 electrons, has 2 fewer electrons. Remember, fewer. The charge means, the positive means fewer. So each calcium atom has 2 fewer electrons. You have 3 of them, which means the total number of electrons that you have lost are going to be 6. I'm going to put 6 electrons here. That's it. This is going to be your oxidation half reaction. Now, going on further and talking about reduction, let's try to write the reduction half reaction. If something was oxidized, something else was reduced for sure. So let's talk about who was reduced. Calcium is out of the picture now because we know it's oxidized. So aluminum. You started with 2 aluminums that have a charge of plus 3, and you ended with 2 aluminums that have a charge of 0. Okay. Aluminums were positive, and now they're 0. So that means the aluminums actually gained 3 more electrons that canceled out this positive 3 charge. So these 2 aluminums have gained a total of 6 electrons. Why is it a total of 6 electrons? Because each aluminum gained 3 electrons to cancel out that plus 3 charge. You have 2 of them, so therefore we gained 6 electrons. And then we ended up with 2 aluminum, 0. So the amount of electrons gained in this case by aluminum were the same as the amount of electrons that we lost previously by calcium. And this is what's so beautiful about redox reactions. The amount of electrons shall always equal the amount of electrons lost shall always equal the amount of electrons gained. With that said, I'm going to end my video here. I'm going to go back to the questions, read the statements, and determine whether the following statements are true or false. So obviously here you're going to have to write these reactions or you're going to have to balance these reactions. All right. Thank you.